Section 4. Parts of the atom. Electrons and the nucleus. Chem Talk. Models in science. In science, it often is necessary to develop models to investigate and explain phenomena. A model is a representation of something in the real world. Scientists use models to investigate things that are too big, too distant, too small, too unwieldy, or too unsafe to observe or test directly. To use a model, the model needs to be similar to the real world in ways that are important for what the scientist is investigating. In this section, you will begin to read about the different types of models of an atom that scientists have developed over the years. Models are extremely important when trying to understand the structure of an atom because atoms are much too small to see. It is important to remember, however, that models have their limitations. They are not able to duplicate the real world. As you work your way through active physical science, look for ways that models can help you understand and explain phenomena. Also, be aware of each model's limitations. The changing model of an atom. J. Thomson's model of an atom. As was noted in this investigation, in the late 1800s, J. Thomson, an English physicist, found evidence for the existence of negatively charged particles that could be removed from atoms. He called these subatomic particles with negative charges electrons. Using this new information, Thomson proposed a model of an atom. This model was a positive sphere with electrons evenly distributed and embedded in it, as shown in diagram A. Using the same evidence, Hantaro Nagaoka, a Japanese scientist, modeled the atom as a large, positively charged sphere surrounded by a ring of negative electrons, as shown in diagram B. These models show that scientists agreed that atoms contain electrons. They also agreed that atoms were electrically neutral. To maintain this electric neutrality, an atom must contain an equal number of positive and negative charges. Millikan determines the mass and charge of an electron. Thomson was able to measure only the ratio of mass to charge for an electron, not the mass itself. The American physicist Robert A. Millikan devised a method for determining the mass of an electron. His famous experiment is called the Millikan oil drop experiment. First, Millikan produced small droplets of oil by spraying them from a nozzle into a box. The tiny mist of negatively charged droplets was allowed to fall between two charged metal plates. It was possible to stop the drops from falling by having the plates exert an upward electrical force on the drops. Millikan was able to calculate the charge of an electron as 1.6 times 10 to the negative 19th power coulombs. He then used Thomson's charge-to-mass ratio to determine the mass of an electron to be 9.1 times 10 to the negative 28th grams. This is about 1/2000th of the mass of a proton. Thomson remarked that these electrons were very, very tiny. Rutherford's discovery of the nucleus. For several years, there was no evidence to contradict either Thomson's or Nagaoka's atomic models. However, in the early 1900s, Ernest Rutherford, a New Zealand-born scientist, designed experiments to test the current model of an atom. In Rutherford's experiment, Positively charged alpha particles were sent as missiles toward a thin sheet of gold. Gold was used because it is malleable and could be hammered into a very thin sheet. Most of the positively charged alpha particles went through the sheet and were not deflected. It is as if they missed the target. This was expected since it was assumed that the atom's charge and mass was spread evenly throughout the gold. Some of the alpha particles were deflected slightly. However, most interesting to Rutherford was that occasionally one of the alpha particles hit the gold sheet and bounced straight back at the source. This was unexpected. The conclusion was that there must be tiny places containing lots of charge and mass. Since the bouncing back was so unusual, it was assumed that the places where all the charge and mass were concentrated were only 1/100,000th of the area of the gold. Rutherford concluded that almost all the mass and all of the positive charge of the atom is concentrated in an extremely small part of the center. He called this center part the nucleus. He used the term proton to name the smallest unit of positive charge in the nucleus. The story of Rutherford's discovery of the atomic nucleus is best told by Rutherford himself. Examining the deflection of high-speed alpha particles as they passed through sheets of gold foil, Rutherford and his student Hans Geiger noticed that some particles were scattered through larger angles than predicted by the existing theory of atomic structure. Fascinated, Rutherford asked Geiger's research student Ernest Marsden to search for more large-angle alpha scattering. Rutherford did not think that any of the alpha particles in his experiment would actually bounce backward. Okay, this is Rutherford speaking. Then I remember 2 or 3 days later, Geiger coming to me in great excitement and saying, "We have been able to get some of the alpha particles coming backwards." It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, a missile, at a piece of tissue paper and it came back and hit you. A physics connection. What was responsible for the wide-angle scattering of the alpha particles and their bouncing back? Well, the major forces involved in chemistry are electrical. They are based on the physics associated with Coulomb's law of electrostatics. The force between two charged particles, Q1 and Q2, is inversely proportional to the square of the distance, d, between them, where k is a constant, and that constant being expressed right here, that's your constant. If the particles are of opposite charge, then the force is attractive. If the particles are of the same charge, then the force is repulsive. Opposite charges attract and like charges repel. The closer the positively charged alpha particle gets to the positively charged nucleus, the larger the force. This causes a larger deflection of the alpha particle. In this investigation, you learned about experimental evidence for the existence of electrons and a nucleus. Think back to when you first heard about electrons and the nucleus. Was it in elementary school? Often, theories about the structures of an atom are presented as facts without explaining any of the evidence that led to the theory. Science involves the accumulation of evidence and the building of a model and theory. It is not memorizing a set of facts. What is the difference between law and theory? Sometimes a word's scientific meaning is different from its everyday meaning. For example, you may say that you have a theory about something when you mean you have a hunch or a guess. You also may say that you obey the law, referring to laws that are written and passed by a government. However, in science, the words theory and law have very different, very precise meanings. In their observations over long periods of time, scientists often notice certain patterns that occur over and over again. From these observations, they develop a scientific law to describe the patterns they have observed. For example, over time, scientists observe that the force between two charged particles is inversely proportional to the square of the distance between them. Coulomb stated this as the law of electrostatics. This law does not explain why all charged particles experience this force, but provides a way of describing what has been observed. Scientific theory provides an explanation for those observations and can be used to predict new phenomena that have not been observed. For example, the atomic theory explains the nature of matter. This theory is not a hunch or a guess. It is the result of years of experiments, observations, measurements, and mathematical applications. The work of many people over many years culminates in a theory, and the subsequent work of many people in many years is required for acceptance of that theory in the science community. With more research, scientists may develop newer theories to replace older theories. As you explore more laws and theories in active physical science, be aware of the difference between a law and a theory. Notice the process by which the community of scientists develop and accept new theories. Understand that laws do not become theories and theories do not become laws.